For A star, remember that we have this heuristic value, right? This heuristic value is given in the table, and I like to write it on top of the node just so I can visualize it easier. So notice that the heuristic value for G is not given because the heuristic value is a measure of how far away the current vertex is from the goal vertex. The goal vertex here is going to be G, and so the distance from G to G is 0, so that's why the heuristic value of G is redundantly 0. Okay, so now remember also that in A star, the criteria for choosing which vertex to go to next is based on this function f of n equals g of n plus h of n, where g of n is the backward cost. The backward cost is the distance from the current vertex back to the start vertex, and h of n is the heuristic or the forward cost. That's how far away that's basically the distance we have to travel from the current vertex forward to the goal, right? Okay, so one way that you can execute A star and keep track of everything is using a table that looks like this. So you keep all the vertices on the left-hand column, and then you have all the iterations as the headers of these columns, okay? So in the very beginning, in the initial stage, we have everything infinity except for A. And the infinity stands for the distance from A, okay? So quite similar to Dijkstra. Okay, and then in the next stage, we need to pop off the node that has the smallest f of n, okay? So in fact, all the nodes in our priority fringe that is not A is gonna have an infinity value as f of n, right? Whereas f of A is equal to the distance of A plus h of A. Distance of A is 0 because we're already at A, and then the heuristic of A is 9. That's 9. 9 is a lot better than infinity, so we're going to pop off A. Okay. So now what happens? I'm going to denote the node that we just popped off with an asterisk, and then we look at all the neighbors of this node, so B and E, and we update their distance values to be from A, okay, the predecessor from A. So for B, it's going to be 1, and for E, it's going to be 3. And everything else stays as infinity. Okay, and so now to determine which of B and E we should go to next, we need to calculate their f value. Okay, so we want to take the min f value. The f value for B is 1 plus the heuristic, which is 7, and that's going to be 8. Let me just circle the heuristics just to make it a little bit more obvious among all my notations. Okay, this is 1. All right, so for E, it's going to be 3 plus 10. The minimum here is 8, which corresponds to vertex B. So that's what we pop off next. Okay, now from B, we have C and F, right? So C is now going to be updated to the distance from A to B plus the distance from B to C, which is 1 plus 2, 3. And then F is going to be a similar scenario. And everything else stays the same. E also has to be in 3, sorry. Okay, so among these 3 possibilities, C, E, and F, which one is the minimum in their F value? So for C, it's going to be 3 plus 4, which is 7. For E, it's going to be 3 plus the heuristic 10, which is 13. And then for F, it's going to be 5 plus 3, which is 8. The minimum is 7, which corresponds to C. So let's pop that off. Okay, and then from C, we can go to F, and F is the only thing. So what is the distance from A to F going through C now? It's going to be C's distance, which is 3, plus the weight of the edge between C and F, which is 1, and that's going to be 4. And everything else stays the same. Okay. All right, and then we need to find the minimum again. So for E, it's going to be 3 plus 10, which is 13, and for F, it's 3 plus 4, which is or 4 plus 3, which is 7. So now we're going to pop off F. And from F, we can get to D, G, or E. Okay, so let's do D. Let's do alphabetical order first. So let's do D. D's distance is going to be F's distance plus 2. That's going to be 6. And then E's distance is going to be 4 plus 7, which is 11. And then G is going to be 4 plus 4, which is 8. And everything else stays the same. Okay, so among these now 3 possibilities, which one do we go to next? Well, for D, it's 6 plus 1, which is 7. For E, it's 11 plus 10, which is 21. And for G, it's 8 plus 0, which is 8. So the minimum here is 7, which corresponds to vertex D. So let's pop off D next. Okay. All right, so from D, we can get to F, G, or H. But remember that we popped off F already, so we can only update the values for G and H. So for G, it's going to be 6 plus 1, which is 7. And for H, it's going to be 6 plus 4, which is 10. And then E stays the same. Okay, so among these 3 values, which one is the smallest? 11 plus 10 for E, 7 plus 0 for G, and 10 plus 5 for H. So the minimum here is 7, which is G. And once we pop off G, we know that we're done because we've popped off the goal vertex, okay? Now, one thing that you should keep in mind about the difference between A star and Dijkstra is that in A star, we're not necessarily updating the distance if the new distance is better than the old distance. We're just updating the distances regardless of whether the old is better or worse, right? Because we are updating once we have a new predecessor. Right? We're updating for all the neighbors of that current vertex instead of just for the neighbors whose current distance is worse than the new distance. And you can see this in action if you look at this E, this, whoops. Oh. Sorry, let me backtrack. Okay, so if you look at this part of E, right, it went from 3 to 11, which is worse, but we did that because E's predecessor was changed when we popped off the new node. Okay, so that's different from Dijkstra. And so if you retrace the path that we took for A star, it's just the order of the vertices as they appear in the column header. That's going to be A, B, C, F, D, G.